Our next topic, and our second to last topic in the entire course, is looking at vectors. And what's nice about vectors is it is so similar to parametric. In fact, you're going to see so much overlap that it ends up being a very easy topic to continue with because we're just pulling a lot of our older knowledge and just adding a little bit as far as notation and some of the wording. So it's a perfect set of lessons to go into the winter break. So with vectors, vectors are special because they show both magnitude and length. And some of this might sound like a physics class when I'm talking about it. A lot of times you will see vectors drawn like this, where you have your starting point. Your starting point is usually written as like a point. So it's usually like a dot. Your starting point is called your initial point. Oftentimes it'll have like a letter associated with it. And then your end is called your terminal point. And it has a length, it has a magnitude, it also has a direction. So it has, I guess I put magnitude and length. I actually was thinking magnitude and direction. You know how far it goes and you know what direction it goes, which is what a vector shows you. A lot of times the notation is written like this. It's written almost like you would write a ray in a geometry class, or sometimes it's written like this, where it has like half of an arrowhead. So that is referred to as a vector. So we could have like vector A, B, meaning we start at A and we go in the direction of B. When we write vectors, there's a couple ways to do it, but the one that you'll see the most often in a calculus setting is to put them in these like pointed brackets. So when you see something like this is a vector notation. The first number is referred to as the horizontal component, which should not surprise you. And the second number is referred to as the vertical component. So your horizontal component is going to tell you if you go to the right or to the left. And your vertical component is going to tell you if you go up or down. So with this particular one, since the horizontal component is 3, then we would say that it moves to the right 3. And since the vertical component is -5, that means it's going down 5. So we get both that direction from a horizontal standpoint and we get a direction from a vertical standpoint. Now, one of the few non-calculus things that sometimes you are asked on an AP test, and I usually put one of these on one of my quizzes because they're easy and it's kind of getting yourself settled, is they can give you 2 points and then they can ask you to write the vector that represents how do we get from one point to the other. So in this one, we're saying we're starting at 3, -1, so that's our initial point, and we're moving to the point 7, -3, that's my terminal point, and it wants to know basically how did we get from one to the other. So to go from A to B, my x value increased by 4. So we would say it moved to the right 4. And my y coordinate went down 2. So the vector that would represent the movement from A to B would be the vector 4, -2. Now, when we talk about magnitude of a vector, we're talking about how long it is. So not only the direction, but how far did we go to get from point A to point B? And to find magnitude, it is going to be basically like you're doing a Pythagorean theorem. You're going to take the x coordinate of the vector and square it, the y coordinate of the vector and square it, and then square root the sum of those two added together. It will always be positive because, again, it represents a length. So if I want to know how far we went to get from A to B, I can take the vector values and say, okay, well, it's 4 squared plus -2 squared, which is the square root of 16 plus 4, which is the square root of 20. And you're basically just doing a distance formula. I mean, that's what's happening here is to find the length from A to B, you are finding the distance we traveled from A to B. So we would say the vector moved 4 right, 2 down, and had a length of the square root of 20. And you can write it as a decimal if you'd like as well. One other notation that I've seen in kind of higher level calculus classes, instead of using the pointy brackets, which years ago I looked up if there's names of the pointy brackets, and I think they called them like angled brackets or something like that. Nothing fancy. Some notations you'll see instead of writing this, so like the one we talked about earlier, 3, -5, is you'll use the lowercase I and the lowercase j, and you'll say that it's 3i and -5j. or sometimes it's written as 3i minus 5j. That notation, thankfully, does not get used on the AP test. It's just too confusing. It starts to look like imaginary numbers, which we don't use. I will say that I have seen that notation in some science courses, and I've seen that notation show up in higher level calculus courses. So I truly only mention it just in case you're going to continue your math and science beyond that. And when you see that show up, that's what that means. These I's and these J's are representing that horizontal using the letter I and vertical movement using the letter J. I'm going to stick to the pointy brackets because that's what I've seen on AP tests. That's what I've seen on multiple choice questions. So we're going to stick with what we're going to be used to. Plus, I think it's easier. So just a real brief calculus introduction, you're going to see that it's very similar to what you would expect as far as our calculus introduction. If I have my position function, so my position function is going to be given as x of t, y of t in these pointy brackets. And sometimes they don't even use the brackets. They'll just use parentheses and still call it a vector. If I want to find the velocity vector, you're going to just derive each component individually. So your velocity vector is going to be x prime and then y prime. So that is one difference that we didn't really have that type of notation in parametric. You will keep each of these as separate components. And then for acceleration, you're going to derive each component again. So your acceleration vector is going to be your second derivative of x in terms of t, and then your second derivative of y in terms of t. So you'll notice with these, you'll have more like pairs of information because we can go from position to velocity, velocity to acceleration. We're also going to get in eventually to going in reverse and integrating. So we kind of derive to go from here to here, we're going to derive, and to go in reverse, we're going to integrate. But we do see it written as two separate components every time. And then the last piece, speed, is actually the exact same formula as what you would have done in parametric. So speed is going to be your dx dt squared plus your dy dt, and it's often written as y prime, although it can be written either way, squared under your square root. And again, speed is always positive. When I take these values and square it and add them together, you're always going to get a positive. So that is exactly the same, whether you're talking basic parametric mode or whether you're talking in more of a vector notation. So those are just kind of the overview. We're going to go through and we're going to practice some questions so you get to see what that all looks like. But this gives you an idea of some basic skills and knowledge you should have coming in.